previously from a functional brain imaging experiment. The idea here was to see what information early visual brain regions may have about hidden or occluded features of human faces. We did an experiment where we showed observers different facial expressions in one of a range of different face presentation conditions with different parts of the face occluded. The key question for us was to see the extent to which early visual brain regions may show similarity in their responses across complementary parts of the face. So across conditions where there's no direct overlap in terms of the bottom-up visual stimulation. And our hypothesis was that this would be possible in the human brain because the human brain obviously has cortical feedback, it has top influences and also lateral connections. Okay, so I have an extra second. We also did something called red. So the way we approached this was we trained a classifier to discriminate emotion based on the brain responses in primary visual cortex for a particular face region, so here the eye region, and then we test the extent to which that classifier can generalize to discriminate emotion based on a complementary part of the face. And if we can do that, then that's evidence of significant degree of similarity across those two conditions where there's no direct overlap in terms of the bottom-up stimulation. These are the results, and basically what we saw was that at least under some task conditions, we did see evidence for that effect. Interestingly, we actually found these effects were much stronger when participants viewed and categorized this stimuli in an implicit manner, so when they weren't actually explicitly processing emotion. So we take this as good evidence for very strong effects of context and shaping early visual processing in the human brain. And in the context of everything else today, it's just a reminder that in biological vision, that's really important.
Hello. So today I got a poster on some early work on a project that we started with some colleagues in Bristol in the Camo lab. Basically how to model an evolutionary arms race with genetic adversarial networks, and in our case this was camouflage. You're probably familiar with the famous example of GANs by Goodfellow and colleagues, that there is a counterfeiter trying to produce fake money and try to fool police trying to tell apart real money from fake money. So we adapted that sort of problem, that example, to what happens out there in nature with camouflage. If you're a prey, you want to evolve camouflage that you stay hidden from a predator, and the predator tries to evolve a better visual system so it can tell apart empty scenes from scenes when there is a target. And here are some of the patterns that we evolved. After 500, 2,500, up to 10,000 training iterations. Quite interestingly, at the end, while they look similar, we used the ash tree bark for all of the background images. They do show a bit of variability, and they were surprisingly effective. So if you can spot the 4 triangles, one of each on those images, or if you're not, then we probably did a good job with that. Yeah. Yep.
Next. Oh. 2 seconds left.
Right, okay. So basically, this work is pretty much to mimic the honeybee eye using a field programmable gauge array. And the idea is, think of how the honeybee perceives or sees the world, and try to model the behavior of this honeybee eye using field programmable gauge array. Initially, what we were trying to do was to have lenses, fisheye lens, that will be able to mimic each of these areas that the honeybee will actually perceive. And we realized that because of the shape of the fisheye lens, some parts get into the edge that we're not able to see very well. So what we decided to do was to put lots of tiny normal sensors, cameras together. And now we've managed to put about 3 together. And what we're trying to do is to use each pixel as one of these lenses that the honeybee has. The inspiration that we've got from this honeybee is the fact that it's able to recognize motion that well, even though if you look at the image, you think it's really blurred, but it's got this capability of being able to recognize motion that well. And it's also got the ability to process information at a very high rate, about 150 frames per second, compared to what human beings can do. So the idea of processing this in parallel, having these multiple cameras which will overlap, process them in parallel, 30 frames per second, so at least we'll have multiple overlapping camera view, which will give us the 150 frames per second, and to be able to process that information, to be able to give us that amount of speed that they use to be able to capture motion. It also got the capability of processing seeing objects with the true color inspiration, and that is one of the things that we're looking at, irrespective of the illumination. It's able to process this information with the true color, whether it's in the dark or the daylight or artificial light. The poster is back there, so if you want more information,